Good morning, everyone. Thank you for showing up for the very first talk of the Tracing Summit. My name is Bruce Dawson. I work for Google in the Kirkland office, just across Lake Washington. It's my colleague George, who also works for Google in the Montreal office, and flew out this week to come to the Tracing Summit. We both work on Google Chrome. That's a little web browser. You might have heard of it. And web browsers are really complex pieces of software. They actually have a lot of the same attributes of an operating system. So you need similarly complex and powerful tools in order to figure out what's going on. We both work on performance, so we make heavy use of Chrome tracing to understand what is going on inside the browser. And we've been doing some work lately to get Chrome's tracing hooked up with Microsoft's tracing infrastructure so that we can get even more insight into what is going on. And that's primarily what we're going to be talking about today. And with that, I'll let George start.
All right, thank you, Bruce. All right, so welcome everybody. My name is George. So a quick overview of what we're gonna talk about today. I'm gonna present quickly an overview of the Chrome architecture, really understand why it's such a complex piece of software to diagnostic. We'll then talk about the built-in tracer. So one of the features of Chrome is it has a built-in tracer that works pretty well. Then Bruce will talk about our work, which is the integration between the Microsoft tracing, ETW, and Chrome's tracing, and then we'll conclude. So you probably heard of Chrome. You also probably know that Chrome is mostly built over Chromium, which is the open source project of Chrome. The architecture of Chrome is a multi-process architecture. A lot of processes are spawned by Chrome, and there's multiple reasons for that. First of all, there's the stability issues. So web pages are more and more complex today. We don't want to have all the web pages running inside the single process. If one of them crashes and there are bugs in Chrome, it happens obviously. We want it to be single to only that specific page so it doesn't crash the entire browser. Also, there's security implications and stuff like that. So that's why we have multiple processes. For instance, there's a single process that we call the browser process. Basically, it's the main one that takes care of all the UI, takes care of all the file reading, etc. And then each page, which is loaded in a tab, usually gets allocated a process as well for security. And then within each process, we have multiple threads. A quick overview for the browser process, which is the main process. So we have a thread that takes care of the UI. That's probably the most important one because that's directly correlated to what we call the jank factor, basically the responsiveness of Chrome. If you slow down that thread, the users will notice it because Chrome just becomes sluggish. There's an I/O thread that takes care of communication between the processes. We will call it inter-process communication. A file thread that takes care of file operation, threads, and many more. So basically, we have a lot of processes, a lot of threads. So we have to have inter-thread communication. We have a notion of posting tasks. If we need to run a certain operation on another thread, we're gonna what we call post a task. We're gonna send that task to a post dispatcher that's gonna send it to the correct thread on where we want to run it. We have the same thing that goes with the inter-process communication. We have IPC directive. So if we need to run a certain piece of code on another process, we can do so by sending an IPC. The big issue there is that makes it much more harder to profile and debug. For instance, execution time allocation. If I'm running a task, but that's been given to me by another process or another thread, how do we allocate and stuff like that? So that notion is not something that we can easily see with a standard profiler or debugger. Right? So that's why one of the features in Chrome is that we have a built-in tracer. It's an open source project called TraceViewer. It's actually independent of Chrome. It's being developed independently. It's part of what we call the Catapult project, which has a lot of small projects about performance, whether the big one is the TraceViewer. There's also one for telemetry, for profiling, etc. So it's completely open source on GitHub, and it's independent of Chrome. Chrome is the biggest client, but I think it's being used also by other projects. So it's a completely open source, and when you go into Chrome, all you have to do is navigate about tracing, and I'll give you a quick demo, and you'll see how it's useful. So it works on all non-mobile platforms. In our case, that means it works on Windows, it works on Linux, it works on Mac, and also Chrome OS. You can also make it work, for instance, on Android. with DevTools. It's just a different workflow, but there's also possibilities for some mobile. And basically, it's going to record C++ and JavaScript method calls and give it to you in a hierarchical view. So quickly about the advantages. Since it's platform independent, it will run on any platform on which Chrome runs currently, at least the desktop one. It's very easy to use. That's the whole point. One of the important things about it is it's super easy to use. So it's not just for Chrome developers. Of course, Chrome developers, we will use it to debug performance issues, but it's just as easily usable by web developers, and I'll give you an example after, so that they can check and see their pages if there are slowdowns, if there are some quirks and stuff like that. Same thing with extension developers and just power users or curious users. And for the format itself, because we can save the traces, it uses JSON, which is very easy to parse and manipulate. So with that in mind, I will give you a quick overview of what it looks like, as well as a small test scenario. So the projector works.
This is the most exciting part of the demo.
Getting the projector to work. All right, excellent. So to start tracing in Chrome, all we have to do is go in About Tracing or Chrome//tracing, which is equivalent, and we're presented with a very simple UI. You see here, there's the record button. That's all we have to do for now. We press on record, we're presented with a dialog. And there we can either choose pre-packaged, if you want, categories, or manually choose the categories we want to enable. So basically, every trace event that's emitted in Chrome is associated to a category, so we can filter them out. Because there's a lot of events that got emitted, so we get to choose which ones are interesting for us. On the right side here are categories that we have to be careful. These may slow down performance because they're slower to emit. The ones on the left usually are very quick, so we can, if you want, enable them altogether. So let's say I'm a web developer. I don't want to play around with the categories. I can just press on web developer. It will automatically enable the ones that were preset for it that we think are important for web developers. You press on record, and then you just use Chrome. Yeah? So basically, you try to reproduce your scenario, obviously, whether it's a performance issue or a layout issue or whatever. And then when it's done, you come back here, press and stop. It's going to do its thing. And then you're presented with your event traces with a timeline. So here we have a timeline, and these are all the events that are being emitted. I can save that trace, and this is very important if we have users that are able to capture their trace events. They can save it, and then they can actually upload it and assign it to a bug. And then developers can take a look at these trace events. Quickly, I'll just give you a quick overview here. So on the left side, you have the different processes. So we have the main process, which we call the browser, and then each tab gets a renderer process. Render is just a word for a tab, if you want. Let's simplify. And on here, we have the trace events. We can use the keyboard shortcuts to zoom in. If you guys ever played Quake, it's the same buttons, A, S, D, W. So you can move around, zoom in, and actually go and see the traces and follow what's happening here. Okay? What I'm going to do is I'm going to load up the trace that I did, and I'm going to show you something that we call the frame viewer. It's because it's very visual. So this is, I'm tracing how Wikipedia's page of Google Chrome gets loaded. Okay? So I can actually follow step by step what's happening here. So you see this is the page being loaded. The green over here will show you what we call the dirty region, basically what's being changed. And this is interesting, so that we see that what, step by step what's being changed while the page is being rendered. So for now, pretty much we're starting to render everything. And then, here. If you go to the next step, you see that the icon, the logo here on the top left gets rendered. Then there's the search page here. Then there's another change to the search field here. And then here, there's something interesting that happens. The whole page gets re-rendered, but if you notice, it's just small changes. There's like a little hide here and a little icon here that gets added. You don't see it, but it gets added here, right there. And that might actually show us that there's maybe a potential performance issue here. It could be the way that the page is being written or the way Chrome is rendering it. So it's something probably we should investigate at some point that we just stumbled on this. There's no real reason why the whole page should be re-rendered just for small changes like that. And then if we continue, you get, again, the whole page re-rendered, but that's probably because there's the whole text here that's being added. And finally, there's the logo here that gets added, and this gets added as well. So web developers, for instance, this is really targeted for web developers, can visually see exactly what's happening step by step, and can probably reproduce that, save it, send it. And the fun part is, since it's JSON format, this could be captured on Windows, Linux, or Mac, and doesn't matter. We can load it up in another version of Chrome under another platform, and then we can still reproduce because it's a self-contained format. Right. So this is one of many aspects of the trace viewer. We decided to show you the frame viewer just because it's very visual and simple to show. Let's hope the projector works again. There we go. Very nice. So other stuff that are interesting in the trace viewer is that it knows about the notion of IPCs, of tasks, so we can actually follow an event. Okay? And this is very important because we have a certain event that happens here that gets transmitted, for instance, to another thread or another process. We can follow that. It will give us a nice little arrow telling us this piece of code here triggered something else in that thread, so we can actually have a flow of event and follow what's happening. And this often is a big problem in the performance because we can't figure out where this came from. So with the built-in tracer, we can have that. And there's other stuff, like another example here. Since we already collect a lot of data, we can have some performance profiling analysis. For instance, if a certain piece of code took here, an example, 54 milliseconds, we can actually see the attribution if it's Chrome, kernel, GPU driver, Java, Android, etc. So we can get some visual information and some more analysis. Yeah.
What does the graph mean?
Sure. So that's a particular operation that took 54 milliseconds. So we can see the attribution. It's a bit slow. So the blue part is what happened inside Chrome. So you see that most of the operation was internal to Chrome. But then the brown part here are kernel, so system calls. Red is GPU calls. So we can see the attribution of a certain operation to the different parts of Chrome and the system, basically. Okay? These ones, they represent, I think they represent call stacks, correct? And this particular trace was taken on Android. One of the advantages on Android is that we can get kernel integration also, which doesn't really exist on Windows, and that's like the perfect introduction for our next section. And I'll let.
Oddly enough, the Chrome tracing is pushing these full features and enough different aspects. There's some parts of it that I have never used, so I've never used that, but I'm guessing what it's like.
So Bruce will talk about our work, which is the integration of the Windows tracing and Chrome. One of the things that we thought was lacking is that if you want to trace on Windows, yes, you get all the Chrome events, but we're missing the system events, the kernel events.
Okay, so acronym time. ETW is Event Tracing for Windows. And this is a set of Microsoft technologies for doing tracing, for recording performance information on Windows. It's actually shipped with Windows since, I think, Vista. And it's actually very well done. I'll give them full credit for that. And it lets you record a huge wealth of operating system information. It's got a built-in sampling profiler. Nice. It also can record every context switch, every file I/O, every disk I/O, every registry access, what window is focused, GPU activity. There's a long list of information that it can record. And then it can take all this information, record it to disk, load it into this viewer, and have all these different types of information on a common timeline. And it turns out that's incredibly valuable. The more different types of relevant information you can get it on a common timeline, the more correlations you can see between them. Oh, this program is waiting on this call stack. Maybe it's because of this disk I/O, which is being blocked by this disk I/O from a completely different process, because it's recording the whole operating system activity. So I think of it as a nicely packaged dtrace with really terrible real-time capabilities, but really nice post-mortem analysis. That's a really terrible description, but it's the best I've got. But meanwhile, I've been using this for a while, but I found the process for recording ETW traces pretty painful, and there were some bugs that I needed to work around. So I created an open source user interface for recording ETW traces, and because I have no creativity, it's called UI for ETW, and that's up on GitHub. So that was the state about 6 months or so ago, and George and I were talking, and we knew that we wanted to integrate Chrome's tracing events with the ETW tracing events. Because as I said, the more different types of information you can get on the same timeline, the easier it's going to be to figure out what's really going on. And we had two basic options there. We can either try and get all these ETW events into Chrome, and we do have some of them showing up in the Chrome tracing, but getting all of them was going to be a ridiculous amount of work. And the other thing we could do is try and get Chrome's events into ETW. And it turns out we have the source code to Chrome, and there's a choke point where all the traces go through, so we decided to focus on that area. So George wrote the code that got Chrome to emit custom ETW events, and then I modified UI for ETW so that it would listen for those events and tell Chrome which ones to emit. So I won't bore you with all the technical details, but this is the UI for ETW, and this is what a user might see. And we can get a customer to use this. They just have to download a zip file, unzip it, and run this program. It'll install whatever necessary prerequisites there are, and then they can start recording traces. So this is both for customers who are hitting an issue and for developers on Chrome. So in order to say that they want to record information from Chrome, they do have to go to the settings dialog. And we've got these Chrome tracing categories here. George mentioned earlier that the different events in Chrome are broken up by categories, so you can control how many events are being emitted. So a user would go and select the ones that they want Chrome to emit. And typically they would do that in concert with a Chrome developer who would tell them, oh, for the issue that you're seeing, this is the information that would be useful. So that gets the UI for ETW side of it working. You just do these checkboxes. You also need to do some configuration on the Chrome side, because tracing can have non-trivial overhead. We want to have it completely off by default, so we need a way to tell Chrome, no, it's okay to listen to UI for ETW and emit events when it tells you to. And because I have a very poor memory, I put a little tooltip in to remind me what to do. And it points out that you need to be running Chrome 46 or later, basically last week's Chrome, on the Canary channel, which is our bleeding edge channel, or later. And then you have to go to About Flags and enable this little switch. So I'm going to launch the Canary browser here. And oh, look, there we are. We are on the Chrome flags page. And if I just search for -ETW, we can see that this is the little configuration area where you can enable this. It's already enabled. If I click there, it's going to disable it. And we don't want to do that. So that's a couple little steps the user has to do, but it's not too bad. All right, so having configured that on both sides, we just click Start Tracing. And we're now recording all these events from the OS and from Chrome to these in-memory circular buffers. And I can now leave tracing running 24/7. It's going to these circular memory buffers. There's not very much overhead. Maybe it's a few percent slowdown of the overall system. So it's not terribly significant. And that's great, because that means you can just keep browsing, and when you notice an anomaly or you hit a situation you want to investigate, then you go ahead and record the traces. So I'll just go over here and start browsing. Not really browsing, just moving between tabs. And I did start tracing, didn't I? Yes. What I'm going to do now is I'm going to close a few tabs.
for you. So when you say you're recording to a circular buffer, is it just an in-memory circular buffer, and when the buffer fills up, it overwrites? Or is it, okay, okay, okay. So,
and it's actually tracing running 24 hours a day for months, a lot of the time, and then I'll just get this one-off glitch in a game I'm working on, or in a browser, or whatever, or some software that I'm using. Record the trace, investigate it, and then write a snarky blog post about the terrible software that I'm forced to use. Something like that. Okay, so what I'm going to do here is close a few tabs, clicking on these to close them. And in Chrome, whenever you close a tab, it updates this list here, which is called a jump list. The trouble is, if you close 3 tabs in a row, you don't want to update the jump list 3 times. That's inefficient, and customers were complaining. So we want to coalesce all those updates. We put in a delay, and then we coalesce them, and I've talked long enough that we should be past the delay. I'm now going to type Control Windows C, which is this global shortcut that tells UI for ETW to save the trace. So we should see saving trace to disk. It's hung right now because it's busy saving. Okay, so it's doing a bunch of work. It's now finished recording the trace. And we actually have 2 web browsers running, the Canary version and the stable version. So it's got a lot of information about the different processes that we're running in the 2 different browsers. And this is one of the little extra features I added. It identifies the processes by type to make it easier to find out what's going on. If you don't know whether you've got a browser process or a render process, it can be a bit more confusing to understand what's going on. So this is a trace I recorded yesterday, which is a known good trace that I already have loaded. And we'll see here that the browser process has the process ID of 4404. So the next step would be, you can rename the trace, demo trace, and then load it up into the viewer. So here's the other trace already loaded up into the viewer. And this is Microsoft's tool, Microsoft's trace viewer. And up at the top here, we have what are called generic events. And this is where custom events, such as Chrome's tracing events that this viewer knows nothing about, will show up. And when we can see down here a list of all the different Chrome processes that were emitting events. So roughly speaking, that's the browser process, there's a GPU process, and then one process for each of the tabs that was open. So quite a large number of them. And if you will recall, 4404 is the browser process, the main process. And we can see that it emitted 6,800 events over the course of this trace, which was all of 13.7 seconds. So it's a reasonably high rate. And if we expand this, and honestly, you can just imagine this works a lot better on a high resolution screen. This is a little bit cramped. It's a big, long list. So the first thing I'm going to try doing is dragging this field over to here. So now we're grouping by the label. So this is a subcategory for the trace. And now I can very quickly find the events that I'm interested in. I'm interested in these jump list events, and here's the jump list post-run update, which is when I close the tab and it says, hey, you should update this at some point. And this is the actual run the update. And I don't know if you can see on the timeline, there's 3 vertical lines when I have this selected, and then 1 vertical line when I have the post-run update selected. The other thing that we're recording, one of the many other things, is UI for ETW actually records input events. So I can drill down into the mouse up and mouse down events, and we can see, hey, there was 3 mouse up events. Doesn't seem to be showing one of them for some reason. But anyway, there are 3 mouse up events, and those correspond to when I clicked on the tab and then released the mouse. And we can see that those are correlated with these post-run updates. So we can get the full stack all the way from the user input to Chrome saying, hey, we should deal with this at some point in the future, to Chrome actually dealing with it. And we haven't even got to the OS-specific events yet. Sometimes it'll keep track of what window's in focus. That can be very useful. We can also keep track of GPU utilization, but I had that turned off. This graph here grabs context switches and tells you exactly how much CPU time is being used by every process on the system. So if the system process comes to life and does some work, I can see that happening. This is the CPU sampling data. But what I want to look at right now is the disk I/O. So I'm going to grab this new graph and take a look at it. I'm going to change its preset to a slightly different view. Show up. So I can now see disk activity from 5 different processes. This is Windows, so there has to be antivirus software running. And there's Chrome, and within that there are some number of processes that are doing disk I/O. Actually, it looks like there's just one, just the browser process. And then we can then go in and see we're doing writes, and it's to this set of files, and there's our jump list icons. So we can see that all that disk I/O is happening right here, and not surprisingly, if we go and click on this, we'll see that it's basically at the same point in the timeline. So this is a pretty simple example. There's nothing terribly complicated going on here, but we've now traced all the way from the input event to several Chrome events, and then gone back to look at the disk I/O. And when this becomes really important is, let's say the user is doing something else that is also touching the disk or is also touching the CPU. Chrome's tracing is not going to know about that. So you need a whole system profiler getting all these events to let us know, oh, the reason that this one write took 700 milliseconds is not because the user's disk is failing, it's because they were running a backup or watching a movie or who knows what else. And I also wanted to just make George's point about how the trace format is cross-platform. This is the same trace, the Wikipedia trace that George was looking at. It was recorded on, oops, I have to load this correctly. It was recorded on a Mac, but I can just as easily load it from the About Tracing on my PC, and I can explore those same frames and see how Wikipedia was painting on his machine. So it's nice to have a portable interchange format for this data. Let me make sure I've covered everything that I wanted to here. So analyzing these traces is very complex. You need to be a performance expert, you need to understand OS internals, and you need to understand Chrome internals. But we've tried to make it so that recording the traces is a relatively trivial process, so we can get traces from our coworkers and from customers in the field. They can just download this tool, record a trace without knowing how it works, and then send it to us. And it was really good timing because I actually got my first, this is hot off the press, details some of this. I got my first customer trace that had both ETW events and Chrome tracing events literally yesterday. So I now know more about an issue I've been wanting to investigate for 6 months than I have ever before. So that feels like a pretty good success. And it's great having the Chrome events and the ETW events. And the ETW events are covering the full stack because we can record call stacks in the kernel and in all these other processes. So it's really pulling in things from some pretty disparate domains, and that's what lets us investigate these problems. All right.
Thank you, Bruce. So just to conclude, we tend to believe that Chrome shares a lot of characteristics with operating systems because we have our own scheduler inside, we spawn multiple processes, etc., which makes tracing and profiling pretty challenging. And one of the most important things in Chrome is we need to make sure that performance never suffers. And this is not something that's easily done. We have to make sure our tools are able to give us the biggest insight possible. So We feature a built-in tracer that's completely platform independent. As long as you can run Chrome on a desktop machine, you should be able to run the tracer. And our recent work, like Bruce said, was to be integrating both ETW and Chrome. We decided to emit the Chrome events into ETW and capture them on the same timeline. And to do that, we developed a front end that's called UI for ETW that you guys can check out on GitHub. Even though we're talking a lot about Chrome, UI for ETW works for any tracing on Windows that you want. It has extra features only for Chrome, but it would work for any tracing situation that you'd like. So we have kept some references for you. And thank you for your time. Questions, comments? We have a couple of minutes for that. Sure. Okay, I'll repeat the question. So I'll repeat the question. Does Chrome only record the trace points in the code, or does it record the talkbacks? The built-in tracer only records trace points. Actually, we can have extra slides here to show. For instance, if you want to emit a trace in the code, we have very simple macros that we use. There's two types of events that you can emit. You can emit an instant event just saying I'm here in the code. For that, you can use the macro trace event instant with either 0, 1, or 2, depending on the number of arguments. You start with the category name. So that's important because that's how the filtering works. You can actually have multiple category names. You can attach a trace event to multiple categories. You just separate them with a comma. Then you put in the name of the function, and then there's just a flag saying what's the scope of it, and that will just emit like an instant trace in your that will be seen in the built-in tracer. You can also have time-based. So you want to trace a time of execution. There's two ways of doing that. You can either encompass this between a begin and an end. So it works very similarly, where you have a trace event begin and trace event end. Or if you want to trace a whole function, you can just use trace event, put it at the beginning of the function, and then it will trace the time of the whole function. This is interesting because in the built-in tracer, it actually appears as a range, right? You'll see the full start and end. These are stuff that we don't get when we're exporting them in ETW. We get them as separate start and begin, but we can infer from that. So we do lose some characteristics of our tracing when we're exporting from Chrome to ETW, such as the time range. We don't get a nice view of the time. We also don't get the IPCs and the tasks. But we get enough information that at least we can correlate that with the system events and be able to infer more. So the example of the jumpers that Bruce spoke about was actually a bug that's been open for a while, and Bruce decided to investigate it. And with the ETW stuff, since it was very Windows specific, the jumpers, he was able to quickly figure out the problem, write a patch to CoolLS, and defer the updating so that we're not putting a lot of pressure on the system when the user's closing or opening a lot of tabs at the same time.
Yeah, the event tracing for Windows, as the name suggests, is Windows specific, so it's not going to give us any assistance on OS X or Linux, with the one disclaimer being that sometimes performance bugs are cross-platform. So if we can find that on any platform using platform-specific tools, then all the platforms will benefit. I'd also say to your question about trace points versus grabbing call stacks or other things, like I said, Chrome we have many different features on the tracing or getting performance information in general. So there is a profiler that'll run on JavaScript, which can give you call stacks, and I believe it's instrumenting the function entry and endpoints for every JavaScript function. But that's a completely different profiler. And there's also a timeline profiler, which is completely different again. It's a bewildering set of tools, again, because it's a very complex problem, and we need a lot of information. And this slide, conveniently enough, shows another technique we'll sometimes use, this scoped UMA histogram timer. You can put that in, and it will actually upload information from the customer's machine, performance information, and then we can monitor that. And because we ship daily builds of the canary branches for people who like living on the bleeding edge, we can actually drop one of these in, leave it in for a week or so, and see what the timing looked like, and then maybe put one in some of its child functions and iterate very quickly on understanding what's going on. So even though we can't put trace events in everywhere because it eventually gets too expensive, we can drop some in temporarily, get the data we need, and then remove them once the investigation has been resolved. So there's a lot of advantages to being able to ship super quickly and get this information back from customers.
Usually within a week we have more than enough data to make a call. Is it worth the performance? Are we actually improving performance or stuff like that? So that's a very nice feature.
Yes. How does the event correlation work? Oh, how does the arrow get drawn? Right. So the question was, how do we do the arrows that connect when a task was requested to be run to when it was actually run? And there's a unique ID associated with each task. So you can actually look in the JSON file and you'll see that unique ID at those 2 points, and that correlates them.
And this is, you don't have to do anything special. It's as soon as you post a task, it gets a unique identifier, and then we can retrace to the other thread or process.
The normal macros.
Just the normal macros will work.
Yeah, the ID is automatically generated, and then it's sent along with the task request, so that on the other end, the macro will post that ID into the trace. So the question is, can you convert other types of trace information into the JSON format for viewing in the Chrome tracing page? And yes, absolutely. There is actually some Linux kernel tracing events, and there is a converter to convert those to our JSON format. So I can say definitively that case because it's been done already. But in general, if your tracing data is compatible, semantically compatible, then it should be relatively straightforward to create the right sort of JSON file that we'll accept.
Yeah, it's a format that's made for the trace viewer. But you can find documentation on that format on the website of Trace Viewer. But yes, it's a new format if you want. Like it's made for Trace Viewer. It's very Chrome oriented, but technically it should be usable for other tracing formats. And since it's JSON, it's very easy to parse and manipulate.
The representation, especially if you see the kernel data, you're going to have very, very large files.
Correct. And this is actually something that, so I'll just repeat the question. If we compared the JSON format that we have with other formats that exist, like CTF, because it's true that since it's a JSON format, it will eventually move. But if you can see here, already, well, first thing we do is we JSON it. Just to we compress it because it's mostly text, so that at least when the user is gonna upload it to a bug, it's not a huge file. I've actually had discussions with the people who actually started the Builtin Tracer, and they're open to explore other formats. They used JSON at the time because it was convenient, and then we just built on it. And it's very hard, obviously, to restart, but it's something that we can definitely take a look at. We're not saying that it's maybe the best format, but it works good enough for us. But we probably do lose some performance issue because of that. So it's something that we'll maybe eventually look at. It was something in my to-do, but later on, to explore other formats, maybe CTF or anything. Maybe the only issue that I have is that we do have some maybe semantics that we have to make sure that we can preserve. Yeah, exactly. We're open to looking at other formats. That's what I'm sure.
And we actually have multiple different importers. So the JSON format is not the only format that we can pull in. It is our default save format. But I don't remember the list of other formats, but I think there's a half dozen or so slightly different formats that the about tracing can load in.
Yeah.
So you are importing in Windows information for the Windows that you are to do them. You have also a trace analysis within Chrome, which is not aware of the Windows model. And Chrome works on Windows and on Linux and on OS 6 and on Android and on. So, what's your view on? Should the analysis? Should the Windows-specific analysis be done in a Windows-specific tool, or should there be a tool that has the Windows model, the Linux model, the OS X model of the OS, as well as the Chrome side, so you can actually do analysis on Chrome? Should that be external to Chrome? Should that be in Chrome? Or
yeah. So to repeat the question, right now we take the events from Chrome, we embed them in Windows, and we use the Windows-specific analyzer to analyze them. And that has to be done on each platform, obviously, independently. Would the other way around be better, maybe? Taking the system events from every OS and importing them in Chrome and having Chrome built-in tracer view everything, if I understand correctly.
Or a third option where you have an autonomous tool.
Or an autonomous tool.
Just doing those models, right?
Yeah.
Require a big difference.
Yeah. So you just actually opened like a big internal debate that we had. I'd say the jury is split on this. We decided to go that route just because it was actually quicker. For instance, let's take just the Windows side. If we want to import stuff into Chrome, Chrome has to be running with administrative privileges, which is just technically there. We prefer not to have it. So another option would be a third applications that will do it, and that's something that we've explored. That we're maybe gonna explore it also in the future. We just took this route because I think it was easier, and the problem also is with the number of events that we want to capture, the built-in tracer is gonna start choking on performance. It's not made to capture that many events. It's not efficient for that, and if you're slowing down the built-in tracer, you're affecting the whole Chrome performance, and then we're gonna skew the data. So that was another problem that we had. But for instance, on Android, and Android is a very good example, we have that. The built-in Chrome tracer gets all the events, including the kernel one, inside of the built-in tracer. And on Windows, we get, I think it's either ECQ or context switches. There was work to start that, but then it was just left as is, and we only have very select ones, and you have to be running administrative with administrative privilege, which is not something you want to do with a browser for security reasons.
I mean, practically speaking, I'd say we should bring in as many OS events as are profitable and as we have the time to do, because there's definitely a lot of value in having them built into the browser's tracing, because every customer has that. But practically speaking, we're never going to get all the OS events into Chrome. It's just too much work. And practically speaking, we're never going to replicate all the features of this analysis tool that Microsoft has created. They're giving it away for free, and it represents however many thousands of hours of work, so I'm going to use it. But basically, we're not going to get dogmatic about that and say we're going to do it all this way or all this way. We're going to cherry pick and get the best of both worlds whenever possible. And as George said, hey, we were able to get this working relatively quickly, and it's already showing some results, and there's a lot to be said for that. And this is probably last question. Yeah.
So I'll repeat the question. So right now, yes, this is Windows specific. How can we make sure that the same problem actually happens on other platforms? That I think we just have to try and replicate manually. I don't think we can really see that here. So depending on the type of bug, if it's a bug really inside of Chrome, normally we will see it on all platforms. But if it's an interaction between Chrome and the OS, then yeah, it might be platform specific. We could, by analyzing the Windows trace, we could probably get an idea if it's an OS specific issue or a Chrome thing. But really the best way is, and when the bug gets created and assigned somebody, they'll just try to replicate it on it. So I think they're manual testing.
Yeah, once you understand the cause of a problem, it's usually fairly straightforward to see if it exists elsewhere. And I put up this graph, not because it's particularly related, but just because I think this is kind of nerdy cool. I have UI for ETW set to use Intel's Power Gadget to monitor things like CPU frequency, temperature, and power draw. So this is actually power draw on the CPU chip over the course of the trace. And this is when it had to update the jump list, so the power jumped up to 20-something watts there. And this is actually recording ETW trace, which was the hardest work it did the entire time. Yeah, nothing useful or important there, but it's pretty. I just have to share.
But power considerations are very important also for us.
Yeah, in other traces this is much more important.
Especially on mobile.
All right.
Thank you very much.
I think we're done. Thank you.